Hello everyone. In today's lecture, let us discuss about half adders. This is a lecture series on digital electronics and I welcome you all for this lecture series. So before entering into half adders, let us see in a digital electronics circuit, we have adders. Why do we need adders and why do we need adders? Have you ever think how your CPU does the addition process? If we consider our processor or the CPU, these are the components inside a CPU. Here we have the ALU. What is the ALU? Arithmetic and logical unit. So we need arithmetic operations as well as logical operations to be done inside this unit. The basic arithmetical operations are adders, subtractors. So we need this ALU require adder circuits. So if we think how a normal addition is being done by a system or a calculator, then the result is using adders. So in digital electronics, there are two types of adders, half adders and full adder. This is the symbol of an ALU wherein we require two inputs and this is the result which is generated. Let us look into half adder. Half adder is a combinational logic circuit which is designed to add two binary digits. What is a combinational logic circuit? A circuit where the present output depends only on the present input. That is, the system do not have a feedback path or the system do not have memory. Such a kind of circuit is known as combinational circuit and the opposite to this is the sequential circuit. Later we'll be discussing about that. And now coming to half adder, it has two inputs and it has two outputs. One is the sum and the other is the carry. It could be realized using XOR gates and AND gate. Now we are going to design a half adder. What are the design procedures? Here the step-by-step procedure is being mentioned. In step 1, we'll be writing the truth table for different conditions. Then for the truth table, we'll be drawing the K-map. And from the K-map, after grouping, we'll be forming Boolean expressions. For the Boolean expressions, we'll be drawing the circuit diagram. Now, let us look into the design procedure step by step. So, first step is to write the truth table. Here, A and B are the inputs. As we discussed earlier, half adder is a circuit which has two inputs and two outputs. So, A and B are the inputs, sum and carry are the outputs here in this case. So, two inputs and two outputs. If you have two inputs, then obviously we'll be having 2 power 2 combinations of inputs. So, if we have 3 inputs, then 2 power 3 combinations will be there. So, here it is 2 input and so 2 power 2 combinations, so 4 combinations, which starts from decimal 0 to decimal 3. And here we have written the binary equivalent. So, actually these are the conditions. If you have two inputs, both the inputs can be false, both the inputs can be true, as well as this A could be false and B could be true, and vice versa. A could be true and B could be false. So similarly, we can have 4 different combinations with 2 inputs. And this is the logical OR operation wherein when both the inputs are 0, sum will be 0 and carry also will be 0. When any one of the input is 1, sum will be 1 and carry will be 0. So for these two, the same condition applies. Then when both the inputs are 1, the sum will be 0 and carry will be 1. It's something like we can take, if it is a normal addition, 1 plus 1 will be 1, 0, 2, which is equal to 1, 0 and 0 will be the sum and carry will be taken to, 1 will be taken as a carry. So first step is to design a truth table. So we have designed and from the truth table we have to draw K-map. So since it is a two variable K-map, two variable system, we require 2 power 2 cell K-map. So 4 cell K-map. So since it is 2 input, we require 4 cell K-map, 2 power 2 cell K-map. Suppose if the input is 3, we require 2 power 3 cell K-map. So here we have the K-map. We'll be drawing the K-map for every single output. Here we have two outputs. One is the sum and the second one is the carry. So for sum we'll be drawing an output, and for carry we'll be drawing a K-map. So for sum, if you see, and when you consider this K-map, this is A and this is B. So this condition will be 0, this will be 1. Here this will be 0 and this will be 1. That is, this will be A bar and this will be A. This will be B bar and this will be B. So when the condition is 0, 0, this is the cell which applies 0 and sum is 0. When the condition is 0, 1, then the cell value is 1. The sum value is 1. So here we'll be marking 1. When the condition is 1, 0, so this is the cell relevant to 1 and B is 0. A is 1 and B is 0. So we have the sum as 1. And for the next case, when both A and B are equal to 1, the sum is 0, and so we have marked 0 here. Similarly, we'll be doing for carry, right? This is the cell corresponding to 0, 0, 0, 1, 1, 0 and 1, 1. Only for the cell with 1, 1, we have the carry value as 1. And for all the remaining 3 cases, it is 0. So this is the K-map. So K-map, we'll be drawing it for every single output. And from the K-map, we'll be writing the Boolean expression. If you see here, we have to group it. Group to the maximum possible number of ones. That is to find the implicants. Here, only one is available, and so this one has to be grouped single. So if you see here, this cell value is A equal to 1 and B equal to 1, that is AB. So we have written AB here. And here again, two ones cannot be grouped together. Already we have discussed about K-map, and in K-map I have given detailed discussion on how to group. Now only these two ones has to be grouped. So this cell value will be A bar and B. Similarly, this cell value will be A, B bar, because this is 0 and 1. That is A bar, A. This is B bar, B. So this cell value will be A, B bar. So we have written it in the sum of product term. So this is the product term, which is separated by the min terms are separated by a sum. And we know this condition, when both the inputs are different, then if we get an output, then that is XOR gate obviously, and so we have mentioned it as XOR gate. Now this is the Boolean expression which we have arrived, and for this Boolean expression we'll be drawing the half adder circuit. So if you see here, for the sum S, which represents the sum. For the sum, the two inputs are A and B, which is XORed. So A and B, if given to an XOR gate, the output will be getting the sum of half adder. Similarly, carry. If you see the carry, it is AB, and which is AND gate. So A and B is given to AND gate to generate the carry. So this is how a system has to be designed in digital electronics. Any kind of system could be designed using the same procedure. First, the conditions has to be written as a truth table. From the truth table, we have to draw K-map. From the K-map, Boolean expression has to be derived, and for the Boolean expression, we'll be drawing the circuit which could be realized. And few other applications are. One is the main and prominent application is using ALU. Then half adder can be used to realize full adder circuits too. It is used in calculators as well as it is used in address calculations, right? Whenever the next address has to be, whenever the program counter of an architecture has to increment the address value, obviously we need adders there. So that is another application of half adder. And here you have the assessment. How many variable K-map is required to realize a half adder? Write the equation for sum and carry of half adder. That is the Boolean expression. I hope you have understood the design procedure of half adder, and thank you so much.